Hi guys, welcome to your third set of notes for your exponential unit. This is on reflections. Hopefully this reminds you a lot of what we did with our quadratics unit, so it won't be so hard. First, we need to remember the exponential functions have this form. F of x equals a times b to the x plus d. We already know that b is the base. And we can find b by finding the Karman ratio from a table or from a graph, and then make a table and then find it. We know from yesterday that our d value is going to shift our function up and down, just like k did for a quadratic, and it's going to tell the truth. Okay, and today we are finally going to talk about a. We know that a is going to stretch or compress our function vertically. And today we are going to talk about reflecting the function over the x-axis. That is also a job. I messed up. X-axis. That is also A's job. Remember, we called that rocks. Reflection over x-axis. So A is very busy. It's in charge of stretching and compressing and then also reflecting. Okay, let's look at an example. The first thing we're going to do is talk about where our horizontal asymptote is. Hopefully you can tell by looking at this equation. Actually, no, we're going to talk about them in alphabetical order. First, you can see we have an A of -1. There's a -1 right there. That is the coefficient in front of our base. Okay, our base is the 1/2. That is what is being raised to the power of x. And then nothing is being added at the end. The d is 0. So there is no shift. So we know that the horizontal asymptote for this function is still on the x-axis. It has not shifted up or down at all. So even though we're going to have a reflection because our a is -1, our horizontal asymptote is not shifting. It's still at y equals 0. That's right in between 1 and -1. It's 0 right there. The next thing we're going to do is make a parent table. So we'll start with x, and then we're going to do the parent, this 1/2 to the x. 1/2 to the x. So my x's are going to be our usual suspects, -2, -1, 0, 1, and 2. And then I'm going to raise x to these powers. It's going to be, sorry, not x. X is going to be the powers. I'm raising 1/2 to these powers. I apparently am still asleep. So I'm just making each of these x's the power x to which I raise 1/2. Now remember that this is something that you're going to be able to do in your head, but I'm writing it out on the video so that you're not like, where'd she get that? Well, this is how. Okay, so I like to start in the middle. Anything to the 0 power is 1. 1/2 to the first power is 1/2. 1/2 squared is, well, I square the 1, I square the 2, I get 1/4. Now I get to do my negative powers. Remember that my negative power raises my base. It makes it the reciprocal with a positive exponent. So if I have a -1, it's going to take this and make the reciprocal with a positive exponent. So it's going to be 2/1, which is just 2. And then same thing for this one. It's going to take 1/2 squared and flip it to the reciprocal, and it's going to be 4/1, which is 4. Okay. here's the thing. If I were to graph this, it would just give me something that looked like this, right? That's what this is. But I don't want that. I want its reflection in the x-axis. So what I'm going to do is multiply all of these by my a value of -1. It's being multiplied by -1. That's my a. So it's going to be -4, -2, -1, -1/2, -1/4. And I'm going to put all of these points under here. So it's going to be -2, -4. That's right there. -1, -2. 0, -1. 1, -1/2. 2, -1/4. And it's going to go. And you can see that we have the reflection of the parent in the x-axis. So I'm going to erase the parent because it's not part of my graph. But it was kind of helpful to visualize what was happening. Okay, so instead of being 0, 1, my y-intercept is 0, -1. My domain is still, well, the x's didn't change. Look, I put in the same inputs. It's still -2, -1, 0, 1, 2. It's still all the weirdo numbers in between those, like √3, √5, √7, 1/2, pi, the golden ratio. They're all in there. So it's going to be all real numbers. The range, well, instead of being y's that are greater than 0 up above here, it's now y's that are less than 0. Because it's under the x-axis. So it's going to be y's that are less than 0. Okay, as far as transformations go, we did not have a stretch or compression yet. That'll be next week. We did have a reflection over the x-axis. That'll be our rocks. And that happened because our a was a negative number. It was -1. If we have a negative a, we are going to have a rocks. Okay, and then we did not have a shift. No shift. That's it. So look at this guy. Okay. So let's go in alphabetical order again, looking at our function. I have the coefficient in front of my base is -1 again. So my a is -1. So I know I'm going to have a rocks. It's reflection day. Okay, my b is 3. That is my base. And my d is 2. That means I'm going to have a shift up 2 units. So my horizontal asymptote is shifting up 2 units. Right there. So that's not y equals 0 anymore. That is the line y equals 2. That is the collection of all the points whose y value is 2. Or y equals 2. Okay. Now we're going to do our parent table again. So I'm going to have columns. I'm going to have my x column and my 3 to the x column. We're going to try to do this one in our heads, guys. So it's -2, -1, 0, 1, 2. If I raise 3 to the 0 power, I get 1. Anything to the 0 power is 1. If I raise 3 to the first power, I get 3. 3 squared is 9. Now my flipper powers are going to flip these upside down. So my -1 is going to flip my first power upside down and give me 1 over 3. My -2 power is going to flip my 2 power upside down and give me 1 over 9. They are reciprocals. Okay? All right, so that's my parent. My parent is going like, right? Like that. But I don't want the parent. I want it reflected and then shifted up. So first I'm going to reflect it and then shift it up 2 units. Okay, so the reflecting happens when I take all of my outputs and multiply them by -1. So that'll be, I didn't leave myself much room, did I? Whoops. -1/9, -1/3, -1, -3, and -9. That's my A. Okay. Now, if I do that, what I'm going to get is this. But that's not shifted up 2 units. So I still have to shift it. So I am going to graph my little table that I made, not from the origin, but from my fake origin. I'm going to make a new fake little origin where my y-axis and my horizontal asymptote intersect. I am going to pretend that this is 0, 0, and I'm going to put it in quotes because it's not the real 0, 0, it's my fake 0, 0. So from my fake 0, 0, I'm going to graph these points. So left 2 from my fake 0, down 1/9. Left 1, down 1/3. I'm just using this table to graph the points from my fake origin. Right or left 0 and down 1, right 1, down 3, right 2, down 9. It puts me 1 off my grid. Okay, so not only has this been reflected, but it's also been shifted up 2 units. Okay, that makes my y-intercept 0, 1, which is kind of weird, but if you think about it, it makes sense. My parent 1 was 0. Okay, it does make sense, and if you want me to explain it, I will, but that would have been a lot to explain, so I'm not going to do it in the video because it'll take too long. So my domain, my x's didn't change. It's still all the numbers you see here, and then all the fractions, all the weird irrational numbers like √3, √7, √5, √2, all of them. Range, okay, so it's going to be under, less than 2. All of my y values are under 2. So its y is less than 2. Transformations. We don't have a vertical stretch or compression yet. That's next week. We do have a rocks. We reflect it over the x-axis because our A is -1. Anytime A is negative, it gets a rocks. And last, we did have a shift. We shifted up 2 units. So if that shift was weird to you, I suggest that you go back and watch the previous video because the previous video is entirely about shifts. So there's some more examples of how to make that fake origin. Okay. All right, everybody, it's the same and different problem. It's our favorite. So one of the first things you're going to want to compare are the bases. And I can already tell that the base for my function 1 is 1/3. That's my base. But for function 2, I need a table to find my common ratio, and then I can use that as my base. So I'm going to make a little table of my pretty points from function 2. So that's 0, -1, and 1, 1. Now, you might be thinking that doesn't make any sense. Like we should be multiplying by 2 or 3 or 4 or something. And you're right, this doesn't make any sense. Like -1, we've never had that be our base. And it won't be in Algebra 1. So what's happening is that this little trick I taught you isn't working because of the shift. So we are going to do something sneaky. We're going to throw this out. It's not working. We are going to make our horizontal asymptote on here. for our function. Boop, 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 boop. Okay, and then we're going to do our little fake origin trick. Okay, so this right here is going to be our pretend 0, 0. Put it in quotes because it's not really a 0, 0. We all know that, but we're going to pretend like it is. And then we're going to get our points from that fake origin. Okay, so from my fake 0, 0, this point is now 0, 1 because it's 1 up. And then from my fake origin, this one is now 1, and then 1, 2, 3. And now I can tell that I'm multiplying by 3. So my R is 3, and that's my base. Sneaky! Very sneaky. Okay, so I've got a base of 3 and a base of 1/3. These are obviously not the same. They are different. Okay, and we know that a base of 3 is going to be growth. And a base of 1/3 is going to be decay. Whoop. Well, that's not on here, so we don't have to worry about it. So let's get some more information about function 1. I'm going to put this in the calculator. Negative 1/3 to the x. I suggest you also do that. Y equals, oh, it's already in here. So make sure you're using this little baby negative. Okay, don't use the big subtraction negative. All right, graph it. So you can see, let me draw it on here, that your horizontal asymptote is right here along the x-axis. Okay, that is not x, that's y. When it's equals 0. Okay, and then you can see the y-intercept is right here. This is the point 0, -1. If you don't believe me that that's it, you can go to your table and you can see it on here, 0, -1. That is the y-intercept. Okay. Okay. So my y-intercept for my pink function, the one that we just looked at on the calculator, was 0, -1. And it was doing this. Right? Kind of missed, but you get the idea. I can do better. Okay, it helps if you make the noise. Okay, so the y-intercept is the same. We said the base was different. The domain is the same because it's all real numbers for both. The range. Ooh, the range. Okay, let me put the horizontal asymptote for the pink function on here. So this one was y equals 0, and this one was y equals -2, right? So for my blue function, the range would be y's that are greater than or equal to -2. Y is greater than, not or equal to, I said that wrong, it's just greater than. Greater than -2, my bad. Okay, and then for the pink function, you can see that it's under. So it'll be y's that are less than 0. So those ranges are obviously very different. They overlap a little bit, but mostly they're very different. Okay, horizontal asymptote, obviously also different. That's not too bad. You can handle that. Okay, let's look at these. So for these, we have to match these up match the functions to their graphs. So my suggestion to you would be, look at these. These two have reflections. This is a rocks, and this is a rocks. Okay, so when we're looking at these graphs, we can see a rocks and a rocks. We're going to deal with those last. So we're going to look at the parent ones first. You can see that this one has a parent, a base of 1/2. So this is going to be decay. Okay, it's going to be going like this. And then this one has a base of 2, so this one's going to be growth. So it's going to be going like that. So based on that, you can see that this first one right next to A is actually A. It's growing, right? It's not reflected, okay? And then if we were to reflect that in the x-axis, we would get this. And this looks exactly like that. It's the same. So I can tell that this one is going to be the opposite of 2 to the x, which would be C. Okay. Now we'll look at D. Look at D right here. It's that decay. D obviously matches this one right here. Okay. And if we reflect that one, we get this, which looks exactly like that. So this one is the opposite of 1/2 to the x. And that would be B. That's how I would do it anyway. I would start with the non-reflected ones and then reflect them, and then, because otherwise it gets really confusing. But it doesn't have to be. Okay, this is going to be pretty straightforward. All we have to do is write the equation of an exponential function that has a base of 1/4. We don't have any requirements for the y-intercept that we have to meet, so we can just write y equals 1/4 to the x. Oh, that was not right. That was a line to the x like that. Sorry. Okay, and then if I want to write the equation for the function that is the reflection in the x-axis, I just have to make my a value negative. So it would be like y equals negative 1/4 to the x. That's it. That's all we have to do. Just don't write the equation of a line like I did. I don't know what I was thinking. I don't have my coffee or something. Okay, if you need help, come and talk to me.